Our next encryption topic is not actually about a system that allows us to encrypt messages. It's actually about a protocol that enables us to share keys. It's called the Diffie-Hellman Merckle protocol. And before we discuss what that is, we're going to discuss the problem that two people may have in exchanging a private key that they can keep away from other people. We're going to review some of the properties of the El-Gamal encryption system, in particular looking at how they use private encryption keys and private decryption keys. We're going to use those concepts to describe the Diffie-Hellman-Merkle protocol, and then we're going to show an example. Alright, so suppose that Alice and Bob want to share a private key for encryption, and just to get this out of the way, Alice and Bob are usually the names of the people who are sharing messages. Oftentimes Alice is the one sending and Bob receiving, or vice versa. In this case, they're trying to share a key. So our assumptions are that they are communicating over insecure lines, which means that eavesdroppers can intercept their communications. So our assumption is anything they say to each other, anything they communicate to each other, that is available to everybody in the world. So what they want then is for any communication that they make between each other to be completely unintelligible to outside parties. So they say stuff, but not stuff that is meaningful to anybody else but Alice and Bob. But we also insist that communication should enable Alice and Bob to end up with the same key. Right? So Alice and Bob can figure out the key from their communication, but anyone else listening in cannot figure out their key. Now, that seems pretty contradictory. However, it turns out that satisfying all those conditions is possible. And what we want to do first is look at some of what happened when we were looking at El-Gamal encryption. Alright, so let's look at the relevant concepts from El-Gamal. We're not going to go through all the details of what that is. If you want to look at all those details, you can look at the other video, look at some of the activities that we did. But I'm just going to give you highlights from what happened in El-Gamal. First of all, of course, we had a public key P, and that just meant it was a prime number, first of all, and all computations were done mod P when we were doing encryption. And then we also had a primitive root mod P, right? And we'll call that one G. And it turns out we could choose any primitive root mod P that we want. So then our message sender would choose a private encryption key. We called that Y back in the old days, and that was between 1 and P-2. The message receiver chooses a private decryption key between 1 and P-2. And the magic of El-Gamal is that the message sender didn't have to know what the decryption key was, and the message receiver didn't have to know what the encryption key was, but they were still able to encrypt and decrypt messages appropriately. In figuring out how they were able to come to those conclusions, we happen to use one of our exponent laws. When we take a power to a power, that's multiplying the power. So g to the x all to the y power is equal to g to the xy. But if you recall, we also use the fact that xy is equal to ix yx when we do multiplication. That enabled us to switch the role of x and y in those exponents. What we're going to do is we're going to take all these properties, we're going to adapt them so that Alice and Bob can share their private key. Alright, so here's what Alice and Bob are going to do to generate their key. And it is going to be very similar to what we did in El-Gamal encryption. So first of all, they're going to give us some public information. And again, public information doesn't mean they're shouting it from the rooftops. It just means that they expect that eavesdroppers are going to pick up this information. So their assumptions when they're making their all their calculations is that everyone's going to know what this is. So the prime number P they're going to use for their mod, and also a primitive root mod P, and as before, we're just going to call that G. So that's the only public information that they're going to share with the world, or with at least the eavesdroppers when they make communications. Alright, so Alice and Bob are, first of all, Alice and Bob are going to communicate to each other what that prime is and what that primitive root is, but they're also going to choose for themselves private numbers. And just like El-Gamal, these private numbers they are not going to share with anybody, not even each other. So Alice has a private number for her and not for Bob, and Bob the same, vice versa. So Alice chooses some number A0 and Bob chooses some number B0, and both numbers, just like in Elgamal, are between 1 and p minus 2. And Alice and Bob are then going to hide their numbers, and they're actually going to hide their numbers in the same way we hid the encryption and decryption keys back in Elgamal. And to remind you how we do that, we use the primitive root g and we stick those numbers in the exponent. So A1 is g to the A0, and then B1 is g to the B0. Those are numbers that are, as you'll see, are essentially going to be public. But they're numbers but the purpose of taking those numbers is hiding A0 and hiding B0 from anybody who looks at A1 and B1. Now, again, what's going to happen here is we're going to choose P big enough, we're going to choose our primitive roots clever enough so that it's going to be difficult for people who know A1 to figure out what A0 is, and also difficult for people who know B1 to find out what B0 is. In principle, again, all you have to do is look at all the powers of G, figure out which one gives you A1, which one gives you B1, and that would tell you what A0 and B0 are, but computationally, that is very difficult, even for a computer. So what Alice and Bob are now going to do is send each other their hidden numbers. So Alice is going to send A1 to Bob, and Bob sends B1 to Alice. And they're doing this over their communication lines, which again, we're assuming are insecure, so people are going to hear those numbers, A1 and B1. But again, as I mentioned in the previous bullet, those numbers will be nonsense to them because they won't be able to figure out what A0 and B0 are. So Alice, once she gets the number from Bob, she's going to take Bob's number and stick her private number in the exponent. So she's going to take Bob's number that she sent to her, B1, and put A0 in the exponent, and then take that computation mod P, and that is going to be her key. And Bob is going to do this very similar thing as Alice did, except with the roles reversed. He's going to take the number that she sent to him, A1, and put his private number in that exponent and take that computation mod P. So A1 to the B0 mod P, and that's going to be his key. And the claim I'm going to make is that both the key that Alice made and the key that Bob made turn out to be exactly the same number. And I'll show you by sort of following the origins of Alice and Bob's computations to see what the key they actually generated in terms of our primitive root G. So let's do Alice first. So Alice, remember, her key was B1 to the A0 computed mod P. Now remember, B1 was G to the B0 mod P, so we can actually replace B1 in our mod computation with G to the B0. And notice now that we have G to the B0 to the A0, and this is a natural place for us to use our exponent laws, or second exponent law, which says that that is equal to G to the B0 A0 mod P. Okay, so that's what her key is. Really, what her key is you take the primitive root, multiply the two private numbers together, and then that's your exponent. Let's see what happens when Bob does his computation. Well, he does the flip side of it, right? He takes Alice's number A1 and takes it to his private number B0 power, mod P. And remember that A1 was actually G to the A0, right? That was the number that hid Bob's private number. So then we get G to the A0 all to the B0 mod P. We again use our exponent law. We get G to the A0 B0. And again, we note that B0 A0 is the same as A0 B0. So they actually computed the exact same key. G to the B0 A0 and G to the A0 B0 they're exactly the same number. So now I want to talk about what about others listening in? Could they figure out what that private key is between Alice and Bob? Well, let's look at what the eavesdropper knows. Eve. They usually write Eve, E-V-E, but Eve's an eavesdropper, so I'm going to spell Eve's name as the eavesdropper gets spelled. So don't give me a hard time. All right, so the only thing that Eve gets to listen to is A1 and B1. And as we mentioned, knowing A1 and B1 makes it computationally impossible for her to figure out what A0 and B0 are, at least computationally impractical. It's difficult to find A0 or B0, and if you can't find A0 and B0, then you're not going to be able to find the key, which is g to the a0b0. You have to find that exponent in order to find the key, and you can't even find either factor of that exponent. All right, so let's go ahead and do an example. So when we do our example, the first thing we have to do is communicate between the two people. Public information, we have to agree on a prime, we have to agree on a primitive root. So our prime that we're going to use is 83. The primitive root mod 83. Again, these are very difficult to figure out ourselves. So we go to Wolfram Alpha. We put in primitive root mod 83. It spits out a whole bunch of them. We pick one. I'm picking 14. That's going to be my primitive root. And so that's the essentially public information. Information that Alice and Bob agree to. Now Alice and Bob have to pick their private numbers between 1 and 81, and they can literally pick any private number between 1 and 81. Let's say Alice picks 75 and Bob picks 40. All right, so the next thing Alice and Bob are going to do is they're going to hide their private numbers, right? Which means they're going to take that primitive root 14 and put their numbers in the exponent. So Alice is going to take 14 to the 75 mod 83 and compute that. Again, I'm going to do that with using Wolfram Alpha. You get 60, so that's the number she's going to send to Bob. And then Bob's going to do the same thing, take 14 and put his private number in the exponent. So 14 to the 40 mod 83, he gets 77, he's sending that one to Alice. So now that they're going to generate the key, now that Alice has the number 77, she's going to take that number 77 to her private number of 75, compute that mod 83, she'll get 65. Bob is going to do the same thing in reverse. He's going to take the number that Alice sent to him, put his private number in the exponent, take that computation mod 83, and not surprisingly, he also gets 65. And that means the shared key between Alice and Bob is the number 65. All right, so now that you've seen that example and seen the explanations, you should be able to do the activities for the Diffie, Hellman, Merckle protocol, and that's on the PDF file included with this video.